Back when we did logistic growth, we studied the integral of a type that we didn't know how to do. It was the integral of 1 over y times 1 minus y over L dy. And the problem with that is that we didn't really know how to split this up. So what we did to try to get this into a different form, at least two fractions, was we split it up into two fractions. So to do that, we actually wanted to, in essence, factor out a 1 over L from the denominator, which with the little algebra converts to L over y times L minus y dy integral. And then I actually split this up into two different fractions. Now what I gave you with that is that you'd end up getting 1 over y plus L minus y, or sorry, 1 over L minus y. And if you move those back to itself, like if you multiply that back out and actually could add them again, you'd see that you get L minus y plus y. L minus y plus y over y times L minus y, which would be the same thing. So this technique is a technique called partial fractions, and it's the big one that we're going to do today. So let's kind of go to a more basic example. Give me a second while I pull it up. Let's say that I have the integral of 5x minus 3 over x squared minus 2x minus 3 dx. Now, what I notice with that is that my degree of the numerator is less than the degree of the denominator. I can't use any of the techniques we did before. I can't divide it. I can't do a U-substitution on the denominator and get something clean that cancels with the numerator. Like if I say u is equal to x squared minus 2x minus 3, I get du is equal to 2x minus 2, and that does not really come up to be anything that we can do with the numerator. I can't really cancel it with a 5x minus 3, and there's no way to get there. So that strategy is out. But we're going to try a partial fraction strategy because I know that my denominator can factor, and that's what's going to happen. When we try to factor it, we get the integral 5x minus 3 over x minus 3 times x plus 1 dx. This is a big clue that we can use a partial fractions strategy to solve this. So what I want to do is I want to split this up into two things. Now, I'm going to tell you right now that those two things are 2 over x plus 1 plus 3 over x minus 3 dx. So can you check to see that I'm actually right about this? Because I'll tell you how to get to the 2 and 3 here in a second, but if I multiply this out, you get 2x minus 6 plus 3x plus 3 over x plus 1, x minus 3, and that gives me back to the 5x minus 3 that we had, over x plus 1, x cubed minus 3, or x minus 3. So integral, and we're kind of right back to where we started, but this one is one that we would know how to do. So how do we get there? Well, I'm going to take this form again, the 5x minus 3 over x plus 1 times x minus 3, and realize this is an algebra technique we're doing. This is actually not a calculus technique to split this into two fractions. What I'm going to do is I'm going to say that is equal to something over x plus 1 plus another something over an x minus 3. Now, when I get that, I'm going to go, okay, I know that those have to be something, but let's actually then add them back together. So if I add them back together, I get a times x minus 3 plus b times x plus 1 all over x plus 1 times x minus 3. Now, distributing the a gets me ax minus 3a plus bx plus b. Okay, we're almost there. We're going to say that this actually has to be equal to 5x minus 3 over x plus 1, x minus 3. Now we don't need to keep writing that denominator down. All I need is that this left side equals this right side, and I want to find an a and a b that makes that true. So let's first check out the x terms. I know that from the x terms, which are these terms, the ax, the bx, and the 5x, I would know that a plus b has to be equal to 5. Then from the other terms, the constant terms, the ones that don't have an x in them, this, and this, let's get those negatives in there, I would know that negative 3a plus b has to be equal to negative 3. Well, this is just a system, and it's a system that's set up if I make the top ones all negative, and I add vertically, I get negative 4a equals negative 8, or a equals 2. If a equals 2, then b is equal to 3, and I can go back up to the a plus b that we had, this one, and just kind of do a substitution. I know that that means that it's equal to 2 over x plus 1 plus 3 over x minus 3. So that's decomposing by partial fractions. Now I'm going to do a little split here, and let's actually evaluate this integral, which should be one of the easier integrals we've done. This is actually just 2 times the natural log of x plus 1 plus 3 times the natural log of x minus 3 plus c. And there we go. Now, right now, today, we are only dealing with denominators. That factor into linear or quadratic factors. We know that we can recognize this because the numerators are always 1 degree less So let's do some more examples of this. That was example 1. Let's call this example 2. Let's do x to the third minus x plus 3 over x to the second plus x minus 2 integral dx. Okay. This is actually, well, I've got degree of numerator greater than degree of denominator. This is not a partial fractions one yet. What I actually have to do is divide the numerator by the denominator. Now, you guys could divide by doing this, and that's fine. That actually might be a little bit easier in this case, because you're going to come up with what you need right away. I am more of a fan of dividing a little bit differently, as you guys have seen. So what I'm going to do is say I want x cubed, but I need to have an x squared in there, and I need to have a negative 2x, because that's what's going to divide out the x squared plus x minus 2. Well then, there was no x squared term originally, so that means it's going to be a minus x squared. Then I need to add an x term to make sure this and this get back to the negative x, and then I have that plus 3 left over. And it's going to be all over x squared plus x minus 2. Let's make that a little bit thicker. Okay, integral dx. Well, this and this divide out to become just an x, because if I pull an x out of the numerator, I can just divide that out. So that's perfect clean x. Then I have minus, if I pull the negative out, x squared minus x minus 3 over x squared plus x minus 2. Now I can just make this x squared plus x minus 2. And then to compensate, I would need to have a minus 2x minus 1. then those can divide out, and I get x minus 1 minus, again, I'm going to factor this negative out and make it 2x plus 1 over x squared plus x minus 2, which I'm going to go ahead and factor that now as x plus 2, x minus 1. So, actually the division might have been quicker in that case, but yeah, I still like my division. So in any case, you divide it and you get this. And this is going to be a partial fractions problem, because if I put this in parentheses and I want to figure out what a's and b's go with that, then I know that a over x plus 2 plus b over x minus 1 has to be equal to 2x plus 1 over x plus 2 times x minus 1. So my next step can be just as easy as multiplying a times x minus 1 plus b times x plus 2 should be equal to 2x plus 1. And then you can set up your system. A plus b has to be equal to 2, and negative a plus 2b has to be equal to 1. Well, when you add those, you get 3b equals 3, b is equal to 1, which means a is equal to 1. And if we take that back to the this thing here, I know that it's going to be x minus 1 minus, this negative is going to distribute, minus 1 over x plus 2 minus 1 over x minus 1. Taking the integral with respect to x. So, integrate, we get x squared over 2 minus x minus the natural log of x plus 2 minus the natural log of x minus 1 plus c. Okay. Last example, sorry, this is number 3. We're going to do a definite integral, 0 to pi over 3. And I'm going to do sine x over cosine x plus cosine squared x dx. Well, I know that I have at least a repeated factor, or a factor in the denominator, so I can pull that out as 0 to pi over 3 sine x over, let's see, we make the cosine x, take that out, I get 1 plus cosine x dx. If I want to split this fraction up, I'm going to have to split it up into a over cosine x plus b over 1 plus cosine x. Integral 0 to pi over 3. And this is just showing my work a little bit differently. Okay, so if I multiply this back out, I'm just going to do this work off to the side. I get a plus a cosine x plus b cosine x, and I want that to be equal to the sine of x. Again, I got those from multiplying this and trying to play like I was going to add those fractions back up. Well, this may look a little bit confusing until you kind of start to realize that if a is equal to the sine of x, then what I would get would be the sine of x plus the sine of x cosine x plus b cosine x equals the sine of x. And we can kind of get rid of those. Basically, I need b to be negative sine x. If b is negative sine x, then these two terms will cancel, and I won't even have a cosine term in the numerator. So I have a is equal to sine x, b is equal to negative sine x, and you can kind of split this up with partial fractions and say that this is equal to the sine of x over the cosine of x minus the sine of x over 1 plus the cosine x. So keeping this going, I'm going to get the integral from 0 to pi over 3 of sine x over cosine x is actually just the tangent of x. And I'm going to split this integral up because I'm going to do a U-substitution minus the integral from 0 to pi over 3 of sine x 1 plus cosine x dx. Okay, so we're going to let u equal 1 plus cosine x, du is equal to negative sine x dx, and this is going to kind of completely replace this the limits on this left side. I'm going to take out the negative, make it a positive, get the integral from 1 plus cosine of pi, that's 2, cosine of 0 to 1 plus cosine of pi over 3 is 1 plus a half, so 2 to 3 halves of, let's see, 1 over u du. Here, if you remember the integral of tangent, the integral of tangent is this negative natural log of the cosine of x, and that's going to be evaluated from 0 to pi over 3. We didn't change those limits. Okay, so get the negative natural log of the cosine of pi over 3 is 1/2. Let's see, this is minus. The cosine of 0 is 1, and the ln of 1 is 0, so this is just minus 0. This is plus the natural log of u, evaluated from 2 to 3 halves. So I get negative natural log of 1/2 plus, I should put my plus c here, plus ln of 3 halves minus ln of 2 plus c. Now we can do better than that. I can split some of these natural logs up to where I have the negative natural log of 1 minus the natural log of 2 plus the natural log of 3 plus the natural log of 2 minus the natural log of 2 plus c. So those go away. That's out. And if I flip the order, I just get the natural log of 3 minus the natural log of 2 plus c, or the natural log of 3 halves plus c. Oh, sorry, there's no plus c here. This is not a definite. This is a definite integral. My bad. So erase those, circle, we're good. Okay, that's it.